Okay. Okay, so we'll start now. The topic of this presentation is overview of secure boot state in the ARM-based SoCs, and this is the second edition of this presentation. No mic here. I'm not. It's only for the video. Okay, so the first edition was taken place like 2 years ago. So now we want to present some update from the research that we have that 2 years ago.
Maybe can you speak up a little bit?
Okay.
We can't hear you.
Okay. Sorry for some. A little technical issue. Okay. Sorry for that. Okay. Okay, so it is an agenda for this presentation. So first, I will tell you who I am and where I work. So say a couple of words about our company. Next, I will just present shortly what do we mean by secure boot in the case of ARM SoCs, and present how the typical implementation and workflow works. Later, we'll show the results from the first edition, so from the 2028. Then we will discuss the two cases that we check for this edition, so the Mediatech and the Rockchip cases. Next, we will summarize the whole presentation, so try to look what was different between those two editions of the presentation, and end with some Q&A session. So this is me. I'm Tomasz Żyjewski, and I'm an embedded systems team leader at 3MDEP. I work there over 3 years now. Mostly, I work on the embedded systems built with the Yocto project. So I try to integrate the update system and the OS creation for the embedded devices. But because I work with the embedded devices, I try to touch different areas of the whole life of that devices. So one of the cases, one of the things I work with is also the system security, and this is the topic of this presentation. So here a couple words about our company. We are from Poland and based in Gdańsk. We are the core boot license service providers since like 2016. Also UEFI adopters since 2018. Yocto participants, so this is the area which I work with from the 2019. Also like the consultants for the FWPD project and IBM Open Power Foundation members. Okay, so now let's explain first what do we mean by the secure boot in the context of this presentation. So here we are focused on the ARM context, which is like the feature of the BootROM, one of the features that BootROM has. Maybe we should call it more like the verified boot, because the case here is that when we start the firmware, the next steps of the loaded images are like verified. The signatures is verified by the previous like part of the firmware. So that's why we should call it the verify boot maybe. So we need to like use some private key to sign the binary. that we put into our machine. Then we also need to take the public key for that from that private key and put it also there. So when we start it, we will be able to verify the signature and decide if it should be loaded or not. In ARM context, in ARM context, we assume that the BootROM is our root of trust. We need to take that assumption because most of them are closed source. Probably it would be better if they will be open sourced, but it is what it is. And yeah, basically the meaning of the secure boot can be different for any given architecture. So if we would be talking about the x86, that would be a little different scenario. Okay, so this is the typical implementation. We have the public key that needs to be written inside our SoC. Different vendors will have some different way to achieve that. So we can, for example, fuse them using electrical fuse. So one time write them in our SoC and later use it every time that we start our firmware. There is also a possibility for the OTP registers. So those are the one-time programmable. So as the name says, also can be used only one time. And one of those two possibilities allow us to make from our BootROM a root of trust, which we later use to expand it to the chain of trust. Next components can use different keys. So in case of secure boot, we talk about the step between the BootROM and the bootloader. And here we have one key that was used to sign the binary and that public key that was used to verify it. But the later steps of starting our machine can use different keys. And yeah, so that would be it. So typically we have let's say our host machine. That should be some secure location and our target device. So on our host machine, we generate some private keys. We build binary and use specific tool to sign them. And later we need to take the public key part of that keys, also the signed binary, and put it in the target device, and then try to verify it. Yeah. So if the verification will be successful, then we will just boot another step. If not, then specific things can happen. Depends on the vendor that we are using. Also, let's say maybe a couple of words about what it is to sign the binary. Basically, what is common between all the vendors probably is that the signing binary means that we take the original binary and add some header on top of it. This header contains the signature of the digital signature and also some specific format at the start, which can be different across some vendors or can be also different within one vendor, but when we are using different signing tools. So if we try to sign our binary, we can always try to dump the first couple of bytes of our signed image and check if everything goes as expected. This is a quick recap from the last edition. So we look at the 11 cases, 5 of them like the NXP, IMX, and Layerscape, ST, STM, Xilinx, and Nvidia looks like were fully open sourced, let's say, and there was non-NDA problems with them, so everyone could try to take the documentation, the needed fusing and signing tools, and try to implement the secure boot on them. We have a couple of cases where there are information that there is some secure boot to enable on that given machine, but it is under the NDA. So we're talking here about the Marvell Armada, Texas Instruments Citara, Qualcomm and Microchips. And also we talk about two SoCs from the Chinese vendors like Rockchip and Allwinner, where like some documentation was there, another were missing. Also, there were some information about tools, but we were not able to find them or maybe use them correctly. Okay, so now I will go through three or four vendors that were listed from the last edition and talk about the differences that was between those 2 years. So now let's start from the NXP. In this case, it's like I think this is the easiest way to start with the secure boot on the ARM SoCs, because the full documentation is there. All documentation is probably like all documentation is publicly available, so everyone can use it. We have the hub for 4, so the high assurance boot mechanism on the platforms that are the NXP IMX 50, 53, 6, 7, and 8M. The application note is here. The only difference between here and there is that those applications are under the free registration to the site. The same is for the IMX8 and IMX8X, which uses the AHIAP mechanism, so Advanced High Assurance Boot. The same for Core Q, and as you see here, the signing tool are available after the free registration. For Marvell Armada, we can look at the manuals that are available on their sites. We saw that for the 38 and 39X families, we have some information that NDA is needed. For other families, like I believe 8K, there is only information that there is a secure boot available, but nothing else there. At the last edition, we present that in the U-boot repositories, we can find some information about how to implement the secure boot on the Marvell Armadas. But now it is not there. It is only on the older releases. So this is another difficult step that need to be taken to find those informations. But yeah, if you will just use this from the 2018 branch, we'll see the information how to implement the secure boot. But yeah, still this is only the theoretical knowledge, and there's no like step-by-step solution how to achieve that. So probably there's a room for mistakes. Nvidia Tegra. Another quick update. Last time we saw that there are some documentations and tools available. We checked that within last year, and it looks like the documentation is some kind of uncertain, because it tells, in one point it tells that the secure boot is available, and they also provides like the flashing tools, the script called flash sh. But in the other place, they just say that the secure boot will be available in the future. Not exactly know, nobody exactly know when the future will be. But yeah, that would be it. Also about fusing, there is additional script for that, but documentation of it is also some kind of updated. There is also like one thread in the forum of Nvidia where someone tried to use it to fuse keys on its platform, and it caused the platform to break, because it looks like not every board can be fused, and before we execute that, we just need to check the serial numbers, because some of them are supported, some not. Also update on Allwinner. So still, we think that there is no official documentation about the Allwinner SoCs which would tell us about the secure boot, and also no official documentation about the secure boot itself. But we found some interesting case on the forum where someone was able to use the NanoPi Neo with Allwinner H3. And he there provides like all the useful links. There's like the 10 or 15 of them, or also the whole list of the verification process. With the link to the SoC tools repository, which contains some tools which need to be used in order to sign the binaries and also fuse the SoC. The one vulnerability there is that in any case when we the one vulnerability is here that if we try to start our firmware which is signed and the verification fails, the platform always goes to the fell mode, which is some kind like the debug mode. And this debug mode can be accessed via the USB port. So if the verification fails, someone could always like plug in the USB, start some minicom, and then read everything from the fuses, or maybe even wipe them. So the solution there for that was just to destroy the USB lines, data lines on that given port. So even if the platform goes into the fail mode, no one will be able to just read anything from it. Okay, so now the Mediatek case. Documentation is provided on the GitLab pages. It is based on the Yocto project project, so the steps there needs to be done inside the Yocto project build system to achieve the implementing the secure boot. But basically, as in other ARM SoCs, the BootROM there is like the root of trust, and later we just achieve it using other mechanism to have the whole chain of trust. So after secure boot, we have the TFA trusted board boot, and then we can use the U-boot feed verified boot to load our kernel image. So if we have all those steps, then we have like whole boot process verified. Yeah, and it also was shown in a couple of reports that the Mediatek BootROM has some vulnerability, which if we like power it in some special scenario, then the BootROM may just skip the process of verification the image and still load the firmware. So it looks like even if we like have the public key in the fuses and also the firmware signed, a public key in the fuses, and we provide the unsigned image and like use this vulnerability, we will be still able to boot our platform. This is a short recap how the secure boot looks on the Mediatek. So we have the BL1 step, which is like the BootROM, which loads the hashed based on the root of trust public key. So this is the public key that we put in the fuses. And calculates also the SHA of the signature of the BL2. So this is like the next step loaded. After that, we compare those two values, and if everything is okay, we go next. And the same, yeah. And then we go like with the, then we load the signature from the BL2, and also calculate the SHA of it, make the comparison, and if everything is once again is okay, we boot the next steps. Okay. And here's the process of enabling the secure boot. It is not clear from the documentation on which SoCs the secure boot can be enabled. The documentation mentioned the MT8365 and MT8395 ones. Different SoCs may have different FUs indexes, so it is really like we need to check those before we try to fuse our fuses in those SoCs. But unfortunately, those information is provided with NDA. in the process of enabling the secure boot, we need to create the two keys, private keys, and provide them to our build system, which sign the BL2 load firmware and also the something called the download agent, which is later used by additional proprietary tools to flash the image inside our platform, which is also described like here. So we have the fuse writer tool. This is another tool provided with the NDA only, which can be used to check the secure boot state on our platform and check if the download agent authentication bits are set. If they are not set, we just need to set them and then provide the public key, which will be fused on the key #0 field. And after that, we will just sign our firmware and use this public key to verify it. Okay, so now let's go to the Rockchip case. The public key here can be stored in fuses or in the OTP, and it depends on which SoC we are using. If the verification of loaded binary will be successful, then we'll just extend our root of trust, so the BootROM, as in the other ARM core SoCs, to the chain of trust. And later, in case of Rockchip, we can use the verified boot mechanism, a fit verified boot mechanism from the SPL to the U-boot and from the U-boot to kernel to provide the whole chain of trust. So basically, to establish it, we need to once again generate some private and public key pair, burn the public key into the fuses or OTP registers, depends on which SoC we are using. Then sign our firmware called EDB loader image in case of Rockchip, which is like the U-boot TPL plus SPL merged into one file. Then configure verified boot in SPL and U-boot, which means that we will use the fit images to verify it from the SPL to U-boot and from the U-boot to kernel, and just flash our signed images. Documentation for Rockchip and as well for Allwinner is hard to find, and if we find any, probably it will be outdated or really short or just not such useful at first. So here we have a diagram of signing the whole, of enabling the secure boot, but basically it is something I just described on the previous slide. And sorry for that, but because of time, we'll just need to skip description of it. And now we can talk about signing code in Rockchip. So code can be signed using one of the two tools, the ERCA sign tool, which can be started on Linux, or secure boot tool, which can be started on Windows. Linux tools can be found on the ERCA bin repository. Windows tools was some time ago was on the repository called tools, but now we are not able to find it. For some reasons, the Rockchip based repositories are maintained in such a way that some things may be missing after some time. But if you use the ERCA sign tool, we can just generate the signing keys, and those keys can be used later with the Linux or Windows tools. And if you use it, and also the ERCA repository provides the ini files, which are the files that can be used to create the mini loader, used later to fuse our keys in the firmware. And basically, any given firmware that we want to sign and use in our SoCs can be also signed with those two tools. There is another tool just to bind the fuses, and we have for that the fuse tool, which is only for the Windows machines. it turns out that when we burn the fuses on the Rockchip SoCs, we also need to provide the voltage for the one of the pins of the SoC. So it is not visible here, but there should be like VCC, VCC, VE, fuse pin, which needs to be powered up when we want to fuse the keys in our SoC. So for that, we need to find some pin that is there and provide the power by ourselves, or maybe our platform has some special like circuit just to enable that. Also, this information comes from another documentation that are hard to find. This is some summarize of enabling the secure boot. So we need to create loader using the boot merger script that is in the RK bin repository. Next, we create the keys with RK sign tool. Next, we need to sign the loader with secure boot tool because from what we know now, only signed with that tool binaries can be later used on our SoCs. We try to sign with the RK sign tool and it doesn't work. And now it looks like this can be hard to achieve because there is no way to download the secure boot tool from what we know now. Then we need to use the fuse tool to fuse our public key in SoCs and use another tool called the RK develop tool, which is in the RK bin repository, just to load the signed loader into our platform and had secure boot enabled. Here's a link for the blog post which describe all of that, containing all of that, what we've done with the Rockchip platforms. So this is the summary of where we are after the second edition. The changes are here about the NXP platforms, where it looks like we now need to register to get the SoCs reference documentation. The Nvidia Tegra looks like the documentation is not really is uncertain and may be outdated. The Rockchip one, we know now that it can be achieved, but still the documentation is not the best quality. The same with the Allwinner. And for the Mediatech, we see that NDA is needed to achieve the secure boot. So this is the summary of the presentation. Looks like our knowledge is expanded over the last 2 years. For example, we know now how to enable the secure boot on the Rockchip. Still, the general principles is common for all the vendors. So we want to authenticate image before we load it. We have some private key to sign the firmware. We need to fuse the public key inside the SoC. And the BootROM is still fitted as the root of trust. All cases use the SHA-2456 as a hash function for digital signatures. And we see that more and more cases the documentation is under the NDA, or the quality of it is really not the best. Okay, here's the way of how you can contact us, and thank you for that presentation. I think we are a little after time, or maybe one question if there is any. Yes? Here?
The question is about in NXP Secure Boot, you have possibility to use ROM in your bootloader to check the firmware blocks. So you can use the Secure Boot of NXP for more components, like fit and U-boot and so on. Do you know if any of those new or the chips you have analyzed other platforms have similar thing, that you can call the ROM and use it as a root for trust of everything?
Okay, so the question was that the NXP provides the possibility to use the BootROM to verify other parts of the firmware loaded in the whole process. And the question is if other vendors also provide such things. From what we know, no, this is only like the NXP case. And yeah, basically that's the answer. And yeah, maybe this one.
How is, given that you analyzed so many vendors, how is the support among the vendors for different types of key with different trust boundaries? Like, for example, like the delegation key for like some like the production in Asia, then you would revoke that key using rollback levels in use cases like this.
Okay, so the question was, I believe, if we try to somehow if there are any process in order to change the key used to sign the firmware, yes? Or
to have multiple keys, like you would hand out one key.
Okay, to have like multiple keys
to one person and to another team, to another company maybe even, and then later revoke it.
I believe that it will be depends on if we have some mechanism in our SoCs to provide more than one public key, yeah. But as we said, those are one time only flashed in the SoCs. So if there is only one place, then I think that it will be only the private key used later for the verification.
And an XP has a few slots. So you have 4 slots, I believe. You can use and you can revoke some of them.
Okay. Thank you.